Hey, welcome back. Today we're going to be discussing centripetal force with tension. I'll add a little bit of friction in with that as well. Today you're going to learn about the centripetal force of tension and how that tension supplies that centripetal force, and how that allows an object to travel in a circular path. First example. 2 kilogram balls attached on a string and swung in a circular pattern at a rate of 10 meters per second. Find the tension in the string. Well, to do this, I'm going to say the sum of the forces, in this case the centripetal force, is equal to the force of tension. So I'm going to get the force of tension is equal to mv squared over r, and in this case I think that's supposed to be 2 kilograms. Let's put a little g up there. 2 times 10 squared well, you know what we're missing here is the radius, so we're going to say with a radius of 3 meters. Now, I'm going to tell you, I had this stuff added in here. I must have not saved it after I had it typed in here and closed it without saving. So that's a little frustrating. But at any rate, 10 squared is 100, times 2 is 200. 200 divided by 3. The force of tension here is going to be about 66.7 newtons. Okay, 3 kilogram ball is attached on a string, and the string goes through a tube with a 10 kilogram mass hanging from the other end. A 3 kilogram mass has to be swung 2 meters out, that's the radius, to keep the 10 kilogram mass from dropping. How fast does the 3 kilogram mass have to be swung? Well, again, I'm going to say the sum of forces here. Let's use a different color this time just for fun. In this case, we've got force of tension again. But what I want you to realize here is the force of tension is being supplied by the weight of the second mass. And that's this right here. So really what we've got is we've got this tube, and we've got this 10 kilogram mass here that's hanging, and we've got this other string with this smaller mass out there, and this mass right here is being swung, and as it's being swung, it's allowing this mass to stay, to not drop. Otherwise that would drop, and that would bring that to the top of the tube. So as we swing it, all right, it allows it to travel in this circular path and to keep this from going down. So this force of tension, as we said, is being provided by the weight of the second object. So for Ft, I'm going to use mass times gravity of this second object, and then I'm going to say mv squared over r. Now, these two masses are not the same. All right, this mass right here is the one that's being swung, the one that's traveling in a circular pattern. This mass over here is the one that's hanging. So we can't simply cancel those two masses out. They're different masses. In this case, then, I'm going to start to plug information in. 3. We want to know the velocity. The radius, they tell us, is 2 meters out. And the mass of the second object is 10. And gravity is obviously 9.8. So we get, I'm going to multiply by 2, which gives me 3v squared equals 98. 10 times 9.8 is 98. 98 times 2 is, lost my pen here, 196. Divide by 3. And v squared equals 65.3. And then v equals 8.1. meters per second. So this object up here is traveling at 8.1 meters per second, which is actually pretty fast. All right, last problem here for the day. We've got this 20 kilogram mass is attached on a string, and the string goes through a tube with a 1 kilogram mass hanging from the other end. So it's very similar to our last problem. The difference here now is we're going to say there's 5 newtons of friction between the string and the tube. So we've added now the tension in the string, which is being supplied by the weight, and now we're adding a frictional force between the string and the side of the tube. So when we go to do our sum of forces equation on this one, we're going to have the force of tension, which is really the weight, plus this force of friction in this case. So I'm going to say mv squared over r equals, and this tension we said was being supplied by the weight of the object that's being hung. This right here, this. All right. And this tension here is mass times gravity, because it's the weight, sorry, a little brain aneurysm there, I guess you could say, plus the force of friction, which in this case they just give me a number, so I'm going to say 5 there. So let's plug in the information we know. This mass that's being swung is 1 times v squared over the radius of 4 meters equals the mass of the one that's being hung, which is 20, times gravity of 9.8 plus 5. So what we get here then is v squared over 4 equals 201. Now I got rid of the 1 because it doesn't do anything here, so I just went to v squared over 4. Multiply by 4, and we get v squared equals 804, square root it, and we find out that the velocity turns out to be 28.4 meters per second. Well, hey, hopefully that was beneficial for you guys. I'll catch you on the flip side. Check that. Let's talk about what you guys learned today. All right. Hopefully you guys learned about frictional centripetal acceleration. All right. About well, we didn't really want friction, we want tension. All right, and how this tension can be, a lot of times is going to be supplied by a string, it could be supplied by a chain, lots of different things. Over the last couple of days we've talked about how cars stay on flat roads, and that was by friction. All right. How to calculate the maximum speed a car can go around a flat turn, and we've discussed that with great detail as well. And then in the last several days we've been discussing why objects travel in circular paths, and that is because of one thing, and that is centripetal force. Now, I hope I catch you guys on the flip side.